So today I'm going to talk you through an example doing Feldspar-Liquid Thermometry, Hygrometry and Barometry. So as always you will find this in the examples folder, and then if you click on Feldspar Thermobarometry, this is this Feldspar_liquid file. So unlike for clinoproxene and orthopyroxene, because the equilibrium tests and the components are so similar for plagioclase and kspar, we use a single function. So instead of calling it like plag or kspar, it's just feldspar. And then you specify whether you're loading in a data frame of plagioclase by saying plagcomps equals, or kspar by saying kspar-comps equals. And then the function won't let you choose a plagioclase thermometer if you've told it you're inputting kspar compositions, for example. So as always, we first need to pip install thermobar if you haven't already done this on your computer. So you would just uncomment this and run this cell. Then I'm actually just gonna clear my kernel so that we start from scratch. Okay, so we're gonna load in various Python things here. And then we're gonna import our Excel file. So we can take a look at what this looks like. So again, if you go to where you've downloaded this examples folder on your computer, and you go to Feldspar Thermobarometry, then you're going to click this Feldspar-Liquid file. And what you can see is we have two tabs along the bottom. We have a plagioclase-liquid example where we have a lot of different liquids here, all with their oxide_liquid. And then we have the same for the plagioclase oxides. And we also have a temperature and a pressure. Maybe these are from experiments, maybe these are from another proxy you have. Similarly, in the kspar tab, we have liquids, and then the feldspar compositions where you've put _kspar here. So you're going to load these in. To start with, we're going to load in plagioclase-liquid. So we're calling the dictionary that we load in outpl. And then from this, we're going to extract all of the inputs as outpl my input, and then also the plagioclases and the liquids as these two data frames. And then we can inspect these to see what they look like. And we can check for empty columns here, and the only column that's empty for plag is manganese and chromium. And you can see that that is because we didn't put anything for these ones in here, and the same for chromium. So that's fine, it's loaded everything in right. The liquids all look good, all the oxides are there. Similarly, we're going to load in our kspar-liquid pairs from this sheet. The difference being when we extract the data frame, we're now looking for things with kspar in the name. And then again, we just want to check that they've read in right. And obviously more elements haven't been measured in the kspar than the plagioclase in this example. Now at any point you want help, you can do the normal help and then PT for thermobar and then the name of the function. So what you can see here is that for calculating feldspar liquid temperatures, you need your liquid compositions as a data frame, and that's what you loaded in using that input function. And then you either need to specify kspar comps or plag comps, depending on whether you want to do kspar or plagioclase thermometry. And then your various equation T choices. You've got one equation for kspar, two equations for plagioclase. You might need pressure for some of these, for pressure sensitive thermometers, and you always have the option to overwrite the water content you gave it in your spreadsheet in the function itself. And it's going to return your Panda series in temperature in Kelvin. So as a first example, say we want to calculate plagioclase-liquid temperatures using equation 23 of Peterka at 5 kilobar. So we specify the function name, specify the data frame of plagioclases that we loaded in. So that was up here, we called it plages, and we call the liquids PL. So we can go here, and then P is 5. So you can see the first one is 1408 Kelvin. We could also use equation 24a, and you can see these are really very similar. So the first one is only 5 Kelvin different. Now you might want to calculate equilibrium tests between the liquid and the plagioclase. And this is following the approach suggested by Keith Paterka in his spreadsheet, where we're evaluating the KD for albite and orthite. And if your temperature is less than 1050 Celsius, you're going to use this value. And if your temperature is greater than 1050 Celsius, you use this value. So we do the same thing as before, but now we're just going to specify ectests equals true. And you can see what that does is, in addition to giving you your temperature, it tells you whether you have passed this anorthite albite equilibrium test. So in this case, it has calculated the temperature and it's seen it's 1400 Kelvin, which is more than 1050 Celsius. So it's telling you it has decided to use the high temperature test, and using the high temperature test, it has failed. You then have the values of the different equilibrium tests along here, as well as the compositions of the plagioclase, the liquid you entered, and all of the intermediate calculations it has done. So first, we might want to filter based on the value of this test. So we can make this variable called ecfilter, and we do that by saying we want to look at the value of the data frame, which we calculated above here, and we want to look at the column pass anorthite albite, and we want to look where that column contains the word yes, whether it used a high temperature or a low temperature filter. So we can run this cell, and you can just have a quick look at what these filters look like. So it's basically just a series of falses and trues. So falses is it didn't contain yes, true is it did contain yes. So then what we can do is we can say, well, we want to make a new data frame, which is the temperature of plagioclase using equation 23, where we have filtered. And now we take the original data frame and we find the locations where it passes this equilibrium filter, so where the values in this were true. And we can run this and we can look at the results, and we can see now all of this column says yes in it, which is what we wanted. Some of these are high temperature matches, some of these are low temperature matches. So we can also add additional filters if we want to. Say, as well as that filter, you also want the difference between the calculated and predicted anorthite component to be less than 0.05, same for orthoclase, less than 0.03, same for albite, less than 0.03. These numbers are arbitrary, but for some reason you might have looked at experimental data and decide that these are useful additional filters. So now we can make a new data frame, which we're going to call filter 2. And we take the original data frame and we say we want the location of it where that first equilibrium filter was true, and then where all three of these are true as well. So we can look, and now we can see we have far less plagioclase-liquid matches. And you could use this technique to filter based on any other equilibrium criteria that you decide are important. Okay, so moving on to plagioclase-liquid hygrometry. First off, we're going to calculate it using equation H of Paterka 2005. So the function is pt calculate Feldspar-Liquid hygrometry. We specify our liquid compositions, we specify our plagioclase compositions, we specify the equation H and the temperature in Kelvin, so here at 1000 degrees C. And we are using the pressure that is from our input spreadsheet. So you can see here that here's a pressure in gigapascals, and we need it to be in Kelvin, in kilobars to input to this function. So we're going to times it by 10 here. You can see you have your water calculated, and by default it returns the equilibrium tests, just because it's important really when you're calculating water content to make sure there is some degree of equilibrium between that liquid and that plagioclase. So similarly we can do that, but specify instead equation H from Waters and Lang 2015. We can run that. Now, because these hygrometers are actually only using the composition of anorthite and albite in the plagioclase, it's not using anything else. You can also, instead of specifying plagcomps equals, just specify X anorthite and X albite. Here we're using constant values for all liquids, but equally you could replace these with columns from your input data frame with, say, the anorthite and the albite content. You can run that. And you can see the outputs look very similar, the only difference being you haven't got plagioclase compositions here because you haven't entered them. You could do the same for equation H of Paterka. So plagioclase hygrometry is extremely sensitive to temperature, and we can demonstrate this using a for loop. So the first thing we do is we set up linearly spaced array of temperatures from 1100 Kelvin to 1200 Kelvin with 10 data points. We then set up an empty NumPy thing, which we're going to fill with water content from the waters equation. So we call H waters. And we're telling it we want this empty array to be the same length as this lin space, and the data type, they're going to be floats, so numbers. We then set up the for loops. We're saying for I in the range of 0 to the length of this. So that's going to do I is 0, I is 1, all the way to the length. These 3 lines just turn off the warnings, which will just tidy up your script a bit. And then finally what we say is the ith value of this H waters is equal to, you calculate Feldspar-Liquid hygrometry. We're using the first row of the liquids just for simplicity. Fix anorthite and albite content, equation H from waters, and then we're using the T from the lin space. So for H waters 0, we will use temperature, which is 1100 Kelvin. We just put the dot here because that extracts the column that is the water content calculated. So you can run that, and you can just have a look. And that's because it's now called H waters. What you'll see is that for the first temperature, the calculated water content was 5.8, and for the last temperature, it was 3.6. So we can plot these values, H waters, against the temperature for the input. And you can see this is what it looks like. And you can use this approach of making a lin space to sort of investigate sensitivity of any of these equations to the input variables. So this is obviously a problem in natural systems. It may well be that you don't know your temperature within 100 Kelvin, and that corresponds to more than 2 weight% water uncertainty. So what we've done is we've set up a function, calculate Feldspar-Liquid temperature hygrometer. And what this does is it effectively iterates pressures and temperatures. So first you take your liquid plagioclase thermometer, and that requires water, and the hygrometer requires temperature. So first we can do the calculation for the temperature with no water. We then input that temperature into the hygrometer and use it to calculate a water content. We then feed that water content back into the thermometer and repeat that for a set number of steps. And you can specify those number of steps with this iteration equals 30. So what this function does is it returns a dictionary. Here we've called it dict.ht. And within this dictionary are stored 2 data frames. The first is your calculated temperatures and water content at that final point, so at that n equals 30 iterations. And then we also output a data frame which you can extract using the square brackets and its name, th evolution. And this extracts the evolution of temperature and water content as a function of the number of iterations. So we can run this, and we can have a look at these outputs. This will run faster on your computer. It's because I'm running this video recording software and my laptop doesn't have enough oomph for all of that together. So what you can see is the calculated TH head, so that's this first one. You have the number of iterations, so here 30. The temperature is calculated. It then gives you the delta temperature, so this is the temperature from the current iteration minus the temperature from the previous iteration. So you can just have a look down here and check that these numbers aren't significant. Same for delta H, and it gives you the H2O calculated. And then as before, it gives you whether it passed the equilibrium tests, all the equilibrium tests, and then all of the input data. And you can look at this th iter variable, and what this does is it gives you the iteration. So we're looking at the first 4 iterations because we've said we want just the head of this data frame. So it tells you for sample 0, so the first plage liquid pair you've given it, the water content it calculates is minus 0.08. The temperature is 1416 Kelvin. For sample 1, so that's your second row, you have 0.17, 14.07, and you can see, so for each sample, you'll see the evolution of water content down here for this sample, evolution of temperatures, etc. So we can plot this. So we're going to plot three subplots. The first one, we're plotting the calculated temperatures and water contents, and then we're plotting the iteration against the column for the first temperature, so here, and the same for the water, sorry. And what you can see is these are your calculated water contents and temperatures. And then as we plot the evolution of temperature against iteration for these three samples, you can see actually we tend to converge within about 10 to 20 iterations. So this gives you confidence that you are converging on a solution. In a very small number of scenarios, you might sort of wobble around forever, and that would suggest that this isn't a reliable way to iterate temperature on water. So finally, we have included plagioclase-liquid barometers for completeness. You should definitely read Keith Paterka's paper about whether this is actually an accurate thing to do, whether plagioclase is a good barometer. The overall summary being it's probably not. But they're here, so you can calculate using this function name, specify your liquids, specify your plagioclases, specify your equation for pressure, and again, you can just calculate the pressures in kilobars, or you can specify equilibrium test is true here, and then you get more of the information out and whether it passes this test or not. Finally, Feldspar-Liquid Thermometry, so very similar, same function name as plagioclase, only difference being you enter kspar comps and you choose this equation. And again, we can run it just like this and we'll just get the temperature in Kelvin, or you can return equilibrium tests as true. And it tells you, sorry, there are no equilibrium tests implemented for kspar-liquid. That's because we couldn't find any in the literature that are relevant. But if you have a relevant equilibrium test you would like to see implemented, please reach out.